all. Thanks for tuning in to Young's double slit experiment. So what we're going to start with is light. Light is a wave, except when it's behaving like a particle. This experiment proves its wave behavior. We're going to draw it like a wave. So waves are going to have nice equal wavelength, and for me, I'm going to imagine my wave is traveling to the right. As it travels to the right, its wave fronts are traveling. That's its crests are traveling to the right, upon which it hits an opening. Now, one way to visualize this is imagine a wall that's blocking a wall of water with a little tiny barrier in between so that water can flow out of these holes, and another wall. Okay, water's going to get into these two holes, or in this case, light. Monochromatic light. I can tell this is monochromatic light because all this light has the same wavelength as I've drawn it. Now, if this were a particle, it could either go through the upper hole or the lower hole, but it can't go through both. But this is where waves are different. Waves can go through both openings at the same time. So, I'm drawing two semicircles, trying to keep the wavelength the same as I draw. And since this light has come from two of these openings, light must also go through here and keep the same wavelength. Oh, that was bad, but you know what I mean. Now, along the center, you'll see that there are places where the light has constructive interference. There are places where the lines overlap each other. What this represents is called an antinodal line. Along this line, you would have a bright spot of light. Along this line, you'd have a bright spot of light. Along this line, you'd have a bright spot of light, and pardon my drawing, I am doing this off the top of my head. And one more. Out here. These bright spots of light, you actually can't see them unless they reflect off something else. This would be considered diffuse reflection for those of you paying attention. So imagine that this light has now hit a sheet of paper. That paper would have light spots on it, which we're going to call maxima, with dark spots in between. This is called Young's double slit experiment, and it shows that light is a wave, not a particle. If a particle were to go through either the top or the bottom, I would either see a particle right below this opening or right below this opening, but not going through both openings at the same time. Imagine if I threw a baseball at this opening. I would imagine that I'd have one baseball at the other side, not a bunch of differing baseballs. That wouldn't make sense. So, next, we're going to look at the geometry and do some math. So, we've reset our Young's double slit experiment, and we're still imagining monochromatic light going through both openings at the same time. But now we're going to do some measurements. So, what we're going to need is the distance between these two openings. We're going to call that D, slit spacing. Notice that D is a distance that should be measured in meters. All right? Next, we're going to have the distance of this opening to the screen. And maybe I'll draw it down here on the bottom so we have enough space in the center. We're going to call this L. The distance of the light source to the screen, L, also measured in meters. Finally, we're going to have spacing. Spacing, assuming that the bright central maximum is in the center, would be how far apart these bright and dark spots appear. So, let's imagine this is my central maximum, around which the bright and dark spots appear. We're going to call that n equals 0, the 0th maximum. It occurs right in between all the other dots in this pattern. Both above and below it, we next have bright spots, which we're going to call the first order maxima. So that's n equals 1, and notice that n equals 1 occurs on both sides. The first order maxima are the bright spots surrounding the central one. Okay, can you guess what comes next? If you guessed second order on both the top and the bottom, you would be right. Yay! Because remember, what these are representing are going to be the bright spots occurring because of monochromatic light going through these openings, just like you would have seen in class. Okay? So, of course, this goes on. N equals 1, 2, 3, 4, 5, 6, 7, not drawing those. This spacing is going to be measured from the central maximum to the bright spot you're measuring would be y, also in meters. So notice we've got meters, meters, meters. One more set of meters, wavelength of light. Since this is not drawn into the picture, I'm going to put it as a little side note out here. We have the wavelength of light also measured in meters. So to tell them apart, let's do it like this. We've got wavelength, slit spacing, bright spot spacing, and distance of the source to the screen. The next equation you see is going to have all the distances put together in one equation that shows how the spacing between the bright spots depends on the other three. So, let's see if we can remember this from the lab that we did. We have y, the spacing between the bright spots. That's going to be related to the wavelength. Bigger waves, like the color red, were spread out farther than the color blue. That's why when you watch the Veritaserum video, the red lines were on the outside of the white dots and the blue lines were in the center. This should be easy to remember because it's just like a rainbow. Red's on the outside, blue's on the inside. Though, to be fair, that's for totally different reasons. Rainbows have red on the outside for refraction. This has red on the outside for diffraction. So, the spacing between the bright dots depends on wavelength. It's also going to depend on how far away you are. Think of it like a projector screen. If I put a screen right here, those dots would be much closer together than they are when they're out here. As L goes up, the spacing between the dots goes up. Finally, we have D. And here's one that doesn't necessarily jive with everyone. Unless you've already done this lab in class, you wouldn't have noticed that as D goes down, Y goes up. Okay, what does that mean? That means if those spacings are really far apart, like D goes up, then you don't notice the red dots being separate from each other. Actually, this is a really good explanation of why you never noticed this before, even though it's a natural thing that occurs with light. What this means is that if my two holes, double slits here, are too close together, then we can see this pattern. If they're too far apart, like bigger than a human hair, you're not going to notice it. That's why you haven't noticed it before. Okay, so we figured out how spacing of the red dots relates to wavelength, length of the screen to the source, and the distance between our two openings. I'm going to add in one more thing. N. N is going to be the order number. N has no units. Actually, just like index of refraction has no units, this particular N has no units either, but this N means something different. This N is going to be order number. And it's telling you which of the numbers it is from the central maxima. Please notice that it does measure from the central maxima, so that, for instance, the 0th order has 0 spacing because that dot is the central maxima. There is no y. So, last part for today, let's figure out how to label one of these diagrams and do that math equation. So, let's say that I took a laser and I shined it through a diffraction grating and it made a pattern that looked like the dots on the screen. Like this, but closer together. At the right distances, I could actually get a projection to look like this. So, let's start by labeling the central maximum. Let's assume that the bright spot in the middle, that's n equals 0. We've got n equals 1 on either side, 2 on the outside of that, 3 on the outside of that, and oops, I've got a 4th over here and you can't see the 4th on the other side. So, okay, we'll live. The central maximum is going to be easy to tell apart from the other two because it's going to be brighter. And as you go out farther and farther, this is going to get dimmer and dimmer and dimmer and dimmer. Okay? So, I know that I've used a red laser. Red has a wavelength of 650 nanometers. I can see the spacing, y, is going to be, what is that? 2.5 centimeters apart. And in order to do this, I held the laser pretty darn close to here. Let's say this is like, I don't know, 5 centimeters. What I want us to figure out is D, slit spacing. So, let's solve some things, but oh gosh, I probably don't want to use numbers that look quite like that because they're not in meters. So, I'm going to convert everything up to meters. That would be 650 times 10 to the negative 9th meters, 2.5 times 10 to the negative 2 meters, and 5 times 10 to the negative 2 meters. From there, I'm going to solve for D using this awesome equation here. Don't know if you noticed this, but I put in here n equals 0. Oh, my bad. N equals 1 because I had measured this distance right here. So n equals 1 because it's the distance between the first and 0th maxima. So, next, solving for D. This would be 2.5 times 10 to the negative 2 equals 1 times 650 times 10 to the negative 9. L is 5 times 10 to the negative 2. But D is on the bottom here. Think to yourself for a sec how you would solve that. How do you get rid of something in the denominator? Well, you multiply by D on both sides. D cancels out. And by some math magic, it's solved. Okay, well, really close to solved. D is at least by itself on the top, or to get it, one last step would be to divide by that 2.5 centimeters number. Dividing both sides by 2.5 times 10 to the negative 2. So finally, this distance. Gosh, if you notice this distance is super small, well, that's totally normal. This is about the size of a human hair. It's why you haven't noticed diffraction or Young's double slit for normal-sized objects. When light goes around you, it makes a diffraction pattern that is so small you can't see it with your eyes. But alternatively, if you have something so small that you can barely see it with your eyes, it can make a visible diffraction pattern. Trade-offs. So, thing to note here, the smaller the opening, the larger and more apparent diffraction you're going to see. That's why for small objects you would get this pattern. For big objects you would not. So, hopefully that helps you guys solve some problems for today. I will see you on Wednesday. Bye!